Thank you so much for the introduction. I'm really glad to be here. So I am going to, as I was introduced, to speak about a wearable kind of technology that we call robotic exoskeletons that some or maybe many of you have seen in the news in the last years. They are becoming more and more popular. And this is good news because these exoskeletons are a challenging technology, but they really can help and most importantly, improve the life of many people that may have suffered different kind of disorders that affect the movement. So I belong to the Human Locomotion Lab. I am the head of this lab in the Spanish Research Council in Madrid. And we have multiple projects in which we cooperate with different teams with different expertises to try to solve this problem of how can we improve the way that we interact with a patient that needs some assistance or some support to recover the function. I am personally more focused on human walking. So I'm going to speak about what is, in my view, the current state of the art on wearable exoskeletons for stroke and for the spinal cord injuries or brain lesions. So briefly, to explain what is a stroke, it's basically when there is a blockage of the blood supply in the brain that results in the damage of some brain cells and in turn results in the abnormal function of one side of the body, in particular the contralateral side to where the stroke took place in the brain. So the impact of a stroke is enormous, socially and economically worldwide. And there are many ways to help patients to recover partially or in some cases even totally the function. In the case of a spinal cord lesion, it refers to the alteration at the spinal cord level that interrupts the pathways of the nervous impulses that control the movement. In this case, we can see a patient with, that has suffered a complete spinal cord lesion that is affecting their ability to control the hip, the knees, and the joints. So she can use a wheelchair for mobility, basically using the arms, and a very practical solution based only on mechanical design can help this patient to stand and to even make some steps by herself, which is important not only for the function, but also psychologically and in terms of a number of different physiological aspects, such as the cardiovascular system and so forth. So it's very important to try to give another alternative different to the wheelchair to these very heavily affected patients. So the good news is that our nervous system is plastic, so there is this widely known phenomenon of neural plasticity, which means that new circuits can be retrained to partially take over and allow the patients to relearn and regain some mobility. And recovering functional walking is a high priority objective according to the literature. So rehabilitation can be focused to try to increase the self-reliance of patients and to allow them to gain some kind of independence. So there is room, as I was saying, for robotics and technologies to help here. And this was, sorry about this video, there is some problem with it, but I think one can see more or less the idea that about 20 years ago, it was discovered that intensive task-dependent training can help to very rapidly allow spinal cord lesion subjects with incomplete lesions to regain mobility. So these professionals, healthcare professionals, can coordinate their movements to help with their strength to reproduce human walking over a treadmill. And this is useful. The problem is that it is not the more ergonomic and safe way to deliver this kind of treatment. So that is where robotic technology started to really help the physicians and the neurologists to try to improve treatment. So basically, the ideas of improving the intensity to engage the patient, providing some kind of feedback, and to allow different ways to guide the forces that mobilize the legs could help. And this also in combination with different kind of additional tasks and trainings in a standard gym in a hospital. So this is basically what exoskeletons have been shown to be useful for spinal cord lesion subjects that require this kind of intensity and repetitive movements. But there are some other problems that we need to tackle. Exoskeletons can be more wearable rather than constrained devices that can be only used in the rehabilitation clinic, and take this kind of shape of a device that you can put with some actuators and some brain that is able to understand how you want to move and to interact with the environment. So there are, of course, nice ideas and some examples that we have seen in Hollywood movies. So these are nice ways to understand and to guide as engineers how we may think of the way that these exoskeletons should look like. But the problem is that one should really understand first how the human movement is produced, and more importantly, what is specifically needed for a specific patient. So we really need to have a different way to think before we really achieve such kind of exoskeleton that can be used very easily on a daily basis. So what I am going to show here is a video of what is, in my view, the state of the art in commercially available wearable exoskeletons for patients. So this is the Wearable Exoskeleton that is produced by a company in Israel. And this is a nice solution that can be worn by a patient for assistance. So this is not designed for training, as I explained before, but this is more a tool that can substitute the wheelchair in some conditions. So it's an excellent example of this kind of technology, but it still has some limitations. So there are some key features that we are analyzing in our lab. First, how we solve the control of the exoskeleton, the algorithms that are embedded in the device, because we really need to look into the nervous system while a patient is wearing the exoskeleton. Otherwise, we are only looking at the surface, at the periphery, and we may be missing some important aspects of how the motor control is being reshaped. And lastly, we really need to make these exoskeletons to be more robust, more versatile to different conditions, and this should be built also as flexible tools that could be used by clinicians, researchers, and others, so that they can really test different control approaches, different ways to treat patients, and so forth. So this is more or less the basic pipeline of ideas that we use to establish our research in our lab. And well, I'm looking more into detail about the challenges. We need to increase the autonomy of these systems that, in a way that they can be used for training in the clinic, but while the patient is walking over ground, we need to increase the portability. We need to include more compliant mechanisms for safety. And we really need to engage the user to really make the user feel that he is doing something useful for his recovery. And finally, we need to make these systems compatible with other kind of technologies, for instance, electrical stimulation of the muscles, and so forth. So here I'm showing a prototype that we have developed. We call this the H2 exoskeleton. It is an overground wearable exoskeleton that is used in this video by an incomplete spinal cord injured subject in a hospital in Toledo, Spain. So he is normally using a wheelchair, and with this kind of device, he's able to walk only with the assistance that is needed for his specific muscle strength. So he has some residual muscle function, which is not the same for both legs. So the exoskeleton has a local controller that is able to measure the interaction forces, basically the mechanics, and based on that, decide what is the amount of force that is required for this specific patient to perform this relatively fast gait for this patient. So this is an example of assisting. There is not really a treatment involved here. Another example of the same exoskeleton, but in this case used for weekly sessions of treatment. This is a patient that suffered a brain lesion, and he had hemiparesis, and he really needed to improve his gait symmetry because he had developed some compensatory mechanisms. So he had hip circumduction and another problem that is called foot drop, which is the loss of the ability to complete efficiently the swing phase without dragging the foot. So basically, this exoskeleton has shown that controlling actively the 6 joints under this assistance needed approach can be useful for therapy. And this particular case that is reported in this paper, we have shown that the patient is able to increase his function in terms of gait speed, symmetry, and the range of movement in the 6 joints. So these are preliminary results, and we really need to be able to conduct multi-center clinical trials to increase the statistical significance of what we are analyzing. And we really need also, as I said, to make some kind of a zoom into the nervous system. So we focus on the physical human interaction, but we need to also include the cognitive physical interaction while the user is learning and is regaining, for instance, muscle strength or the ability to perform a coordination of muscle contraction. So for that, we initiated 2 years ago a FET Open European project. This is FET Open stands for Future Emerging Technologies. So this is a project that is basically focused on how to exploit sensory motor interaction and how to really build a symbiotic exoskeleton. So for that, we are collaborating with a number of different institutions. And we are putting together different Bioinspired blocks into our symbiotic control architecture. I will not go into detail, of course, but we are including cognitive mechanisms, basically monitoring brain signals when patients use these kind of exoskeletons, including artificial intelligence for adaptation of behavior, some detection of features that are timely required for control, and some kind of imitation of the reflex-based control that we have at the level of the spinal cord. I will focus a little bit more on these 2 aspects, or is one very innovative function that we are integrating. So we are developing a tool in which we are able to predict the forces at the lower limb joints that are the result of the contraction of the muscles of the patient. This is really something new. And I'm going to explain a little bit how this works. So this is the integration of a model of the musculoskeletal system that can be personalized to a specific subject. So this is developed in an open simulator called OpenSim with the contribution of many people worldwide. And we have developed a model of the lower limb that includes the musculotendon system, the muscles, and it accounts for the translation between the activation of the muscles into the excitation that is produced when muscles activate to transform that into muscle activation, and also computes the kinematics or the movement and transform that into information about the musculotendon structure. So with that model, we can predict in real time the muscle forces that will result in moments at joint level. So it seems quite complicated, but the nice thing is that we can use this in runtime while a user is wearing the exoskeleton. So for the first time, we are able to not only measure the electromyographic signals, but we can predict the joint movements. And this will be very useful for clinical application. So this is the last slide in which I will show how my colleague is using the exoskeleton. And we can use this in runtime as a diagnostic tool to immediately know how he is contributing to the movement and how much does the exoskeleton needs to support him. And you don't need a very complicated motion analysis lab as usually would be needed. And with this, I finalize the talk. I would like to bring the attention to the website of the project, and thank you.